Welcome to Wednesday, July 29th. Today's lesson is going to be on your iMaths webpage. It's lesson 2.2, which is topic 2 in the IB syllabus. And we're going to be learning about function notation. All right, our objectives for today are how to use this notation f of x. And we talked a little bit about that yesterday. How to find the value of a function at a point. Okay, when you're finding the value of a function, that's the same thing as finding the y value. Means the same thing. Okay, using function notation in graphs, how to add and subtract functions, which is just like adding and subtracting equations. How to solve an equation that has a function in it. Now, some of the prior knowledge that you need in this particular section are knowing about these different types of functions. So you all know about linear functions pretty good. Okay, quadratic functions, that's equations that have an x squared in them. Now, cubic functions you might be a little bit rusty on. And reciprocal graphs, I don't think you did last year because of the shutdown. So some of those we'll be getting to in more depth. So if you don't have a real good understanding of them now, you don't need it. Okay, we'll get to that here in the latter part of the unit. And then how to solve quadratics, which is something you've also done before in Algebra 2. All right, let's take a look at the first section of this chapter, which is finding or introducing f of x and finding the value of f at a value. Okay, so we have three functions here. The first one's a linear function. The second one's a quadratic, looks like a parabola. And the third one is a cubic, which kind of looks like a cooked piece of spaghetti. That's what a cubic looks like. All right, so in all of these, the function y is defined in terms of the variable x. So by plugging in a number for x, we can get a value of y. And y is the same thing as writing f parentheses x. These two things are just notation that mean the same thing. So when we change the x value, it changes the y value, which means the y value is dependent on the x value. Okay, we can use different sorts of notation to refer to these functions. So as you can see, I can rewrite y equals as f of x. Means the same thing. Okay, I can name, if I have another function, I've got to use a different letter. I can use any letter I want in the alphabet. So each time I have a new function, I change the letter. Okay, what do these actually mean? So the function called f, that's its name. It's like we just named it Fred. Okay, f is defined in terms of the variable x. That means when you put a number in for x, you get a number out. That's what the function does. So to work out a value for f, all you do is substitute x into the equation. All right, so if our equation is 3x plus 2, okay, the notation makes it very easy to show the value of a function at different values of x. So by taking out the letter x and putting in a different number, we can get values of that function at various x values. So if x is equal to 2, all I do is just substitute 2 in, and I do the math. Okay, so the thing that you got to remember is this is the value of the function. Okay, it's the y value when x is 2, or it's the value of the function. This does not mean f times 2. Okay, that is not even, because sometimes in algebra we write a letter next to a number and it means multiply. Not in the case of function notation. All right, so it's easy to show the value of a function at different values of x using this notation right here. This is the y value when x is negative 1. This is the y value when x is 310. Okay, when I just change the letter, that just means you're taking whatever the input is, and in this case it would be 4, And instead of putting it in function f, we're putting 4 into the function that we labeled g. Here, this says take -5 and substitute it into the function that we called h and get the corresponding y value. So on this next page, you have 3 functions, and your instructions are to find the value of these functions for different inputs. Okay? And then it says give your answer to 2dp. dp just stands for decimal points. All right, so pause the video, okay, work these 8 problems out, and then we'll come back and check your work. All right, here are your solutions. All right, now let's take a look at the graphs of these functions. So the graph of a to graph a linear function, one is, this is in slope-intercept form, so you could have just used that, okay? The y-intercept in this case would have been 2, and then this slope is 3, so that means 3 up, 1 right, or 3 down, 1 left. So 1, 2, 3, 1 to the right, or 3 down, 1, 2, 3, 1 to the left. Okay, and that would graph it. Okay, the way that it's graphed here is using the intercepts. All right, so if you want to find the x-intercept of something, to get the x-intercept, you let the y equal 0. So I'm going to take out that letter y, put a 0 in, and solve this equation for x. Divide by -3, or 3, excuse me, and that is my x-intercept, -2/3, 0. Okay, to get the y-intercept, you're going to let the x variable equal 0, and then here's our y-intercept, and then just connect the 2 points. Okay, or you can log into Desmos and plug in that equation. Y equals 3x plus 2. And there's our graph. All right, now we're going to graph the parabola here. And there's lots of methods, okay? So we're just going to keep it simple for this one right here. So we're going to use the same method. We're going to find the intercepts, okay? So I'm going to first get the y-intercept. So I'm going to let x equal 0. Okay, so that's easy. Take out the x, I get x squared. So my y-intercept is going to be -10. When we sketch a graph in IB, what that implies is that it'll have some of the important features on it, but it doesn't have to be super accurate. Now, some of these graphs are pretty straightforward to graph. So, for example, 3x plus 1. Well, that's a linear function. So that's simply going to be a line whose slope is 3 and whose y-intercept is 2. Okay, so that one we can graph really quickly. Okay, so I found we can graph it, like I said, using slope-intercept. So the slope is 3 up, 1 right, and our y-intercept is 0, 2. Or another way you can graph a line or graph any function is get where it crosses the y in the x-axis. So I found to get the x-intercept, you let y equal 0, and then you solve the equation for x. Okay, remember, f of x is the same as a y. So I just took that out, and I put 0 in its place, and I solved it. So that's where it crosses the x-axis. And then, obviously, if we plug 0 in for x, this turns into 2, and 0, 2 would be our y-intercept. Okay, and there's our graph. All right, now let's take a look at the second graph. That is a quadratic because the exponent is the largest exponent up there is a 2. All right, so quadratics, when we graph them, you recall from last year, if the coefficient a here, okay, if this, whatever's in front of that is positive, then the parabola opens up. Okay, if what's in front of the square term was negative, then the graph would open down. So I know this parabola opens up. Now, to graph it, there's lots of different ways. One way is you can find the x-intercepts by factoring it and solving it. All right, so if I was going to graph this, I know it opens up, so I'm going to get the x-intercepts. So I take out g of x and I just replace it with y. It's the same thing, okay? X squared plus 3x minus 10, okay? And I want to find the x-intercepts, I'm going to let y equal 0. And then I'm going to solve the quadratic for x. So now I have this quadratic equation that I want to solve. There's lots of methods of solving quadratics. Quadratic formula, factoring, completing the square. All right, this one looks like it's pretty easy to factor. So I'm looking at, I call it the factor game. I'm looking at what two numbers multiply together to give me negative 10, and at the same time add together to give me 3. Well, positive 5, negative 2 work. So 5 times, those two would give me negative 10. When I add them, I get positive 3. So the shortcut for graph or factoring this is going to factor into two binomials, x plus 5 and x minus 2. Now to get the x-intercepts, we set each one of those equal to 0. So hopefully this looks familiar. And my one x-intercept is negative 5, and my other x-intercept is positive. All right, now we're going to get the y-intercept, which is really easy because all you do is let x equal 0. So this just becomes y equals 0 squared plus 3 times 0. So my y-intercept. So now I know this thing opens up, so I'm just going to sketch it over here, and then we'll see what the authors have. Okay, it goes through negative 5, 0, 2, 0, and it goes through negative 10 on the y-axis. So this isn't a really great drawing because it's not to scale. All right, now when I draw a parabola has a midline that's halfway between these two x-intercepts. Okay, so halfway between negative 5 and 2. All right, so from negative 5 to 2, that's 7. So half of 7's 3.5. So it's going to be 3.5 units from here. Oh, about there. And that's going to be the line of symmetry for my parabola. Okay, so the lowest point of my parabola is going to be somewhere on this green line. I don't need to know where it is right now because we're just sketching this. But I've labeled the other parts that are important. So I know that the two sides of this parabola are going to look even. So if that was my left side, or my right side, then my left side looks something like that. And that's my sketch. All right, now Desmos is a great tool for sketching. So if we just type that in, we can type it in as either y or we can type it in as g of x. It doesn't matter. All right. So I'm going to type it in as y equals x squared plus 3x minus, zoom out a little, and there's our graph. Okay, you can see where it goes through. 2, negative 5, there's the y-intercept. So that's exactly what the authors did as well. All right, now the last one is a cubic. Okay, so a cubic equation, that's a base cubic equation. Okay, now if you wanted help graphing a cubic, well, just to get an idea of where it goes through, you can just make yourself a chart and just pick some numbers. So I could pick like -1. So this would be -1 cubed. So the point negative 1, negative 1 is on the graph. Okay, if x is 0, then 0 cubed is 0, so 0, 0 is on the graph. If x is 1, 1 cubed, 1, so the point 1, 1 is on the graph. And then that gives you a rough idea of what it looks like. Okay, you could do more points if you wanted to be more accurate too, etc. All right, there's our line, and I just rearranged it so that we're used to the variable being first with a line. So I just rearranged it. That tells me my slope is 2 down, 1 right, and my y-intercept is 8. So I got 2, 4, 6, 8, and now my other points are going to be 2 down, 1 right. Okay, join those with a line, and you got your graph. All right, next we've got a quadratic. And what makes this quadratic have a little bit more work is that the term that is on the the quadratic term, which is the term with the square, it's not a 1 like it was in the earlier example, the one prior to this. Okay, this is something other than 1. So our factoring is a little bit more involved. Okay, there's a lot of ways to factor this. The reason I want to factor it is I want to be able to find the x-intercepts. Where on the x-axis does this parabola cross? So the method that I use is what's called the box method. So I drew this 2 by 2 box over here. The leading term goes in the upper left box, and the constant term goes in the lower right box. Then I do something similar to what I did in the other one in terms of what I called the factor game. All right, now since this is not a 1, I actually, to get what the number that I want them to multiply together to be, I take 2 times negative 12 right up here. That's negative 24. So I'm looking for two numbers that when I multiply them, I get negative 24. And at the same time, I want those same two numbers to add together. All right, they're going to multiply together to be negative 24, and I want them to add together to be negative 5x. So we got negative 8 and 3. So what I'm going to put in here is negative 8x and positive 3x. So these two, when I add them, give me negative 5x. Now, to factor this, you're going to take each row and each column and factor out whatever the greatest common factor is. So this starts with a negative, so I call that a leading negative, which means I'm going to factor out a negative value, and the largest factor between 8 and 12 is 4. Up here, the only common factor that there is an x. This is an x squared, and that's an x. So I can pull out 1x. Now I go vertically. Okay, the GCF of 2 and negative 8 is going to be 2. I got an x squared and an x, so the greatest factor I could pull out is an x. And then here, the GCF of 3 and negative 12 is positive 3. Now I can factor this. X minus 4 is one factor, and 2x plus 3 is my second factor. Now I can solve each one of those for 0, and that's going to tell me the x-intercepts. All right, so we can plot those points. We got positive 4, 0. We got negative 1.5. And then I know my line of symmetry is going to be halfway between those two numbers. So to find halfway, and again, this is just a sketch, so it doesn't have to be super accurate, but I took 4 plus negative 3 halves, added them up, and divided that by 2. Okay, so here's 4 minus 3 halves, which is 5 halves. 5 halves divided by 2 is 5/4, which is 1 1/4. So this is the line at x equals 1/4. Now the y-axis is real simple, or the y-intercept. To get the y-intercept, you're going to let x equal 0. Okay, so my y-intercept is going to be 2 times 0 squared minus 5 times 0, which is simply going to be negative 12. So it's going to cross the y-axis at 0, negative 12. So I plot that, and then I'm going to sketch my graph. All right, so there's my negative 12 y-intercept. Remember, this line here cuts the parabola in half, so the vertex of the parabola is going to be down here somewhere. Oh my, that's pretty bad, but I'm not going to erase it. You get the idea. All right, so that was the first two. Okay, this next one has 3 terms in it. That means it's going to have 3 x-intercepts. If we were to multiply this whole thing out, this would be a cubic. The largest exponent would be a 3. All right, now, just a basic thing about a cubic. The number, this is what we said a cubic looked like, okay? That's the basic form of a cubic. These curves right here, see there's 2 curves in this. There's always the number of turning points. This is called a turning point right here. That's called a turning point. So this thing has 2 turning points, and the number of turning points is always 1 less than the exponent. All right, so that's how I know there's 2. The other thing that we know is when the exponent is odd, the ends of the graph are going to go in opposite directions. So this tail of the graph and this tail of the graph go in opposite directions. If it was an even exponent, then the tails of the graph go in the same direction. Both are going up or both are going down. So I know that this graph is going to look something like that. Okay, the reason I know it doesn't look like a cubic going this direction is because if I was to multiply this whole thing out, the term in front of the x would be positive because there's no negatives in here. So negative x just looks the other direction. So getting the x-intercepts of this is pretty straightforward. Okay, this first term is going to give me an x-intercept of negative 2. That makes that 0. This one's going to have an x-intercept of negative 5. And this is going to have an x-intercept of 3. Okay, so I'm going to graph those. So there's my x-intercepts. Now to get my y-intercept, I let x equal 0. So this would become y equals, so that's just 2 times 5, 10 times negative 3. That's going to be negative 30. All right, now I know that this is going to look like this graph up here, and it's going to go through negative 30. Now I'm not going to count out negative 30 boxes here. Okay, so this is not to scale. I'm just going to say, hey, that's negative 30. This one was our 3, 2, 0, and I'm going to sketch it so it looks like this shape up here. All right, so that means this one's going to have to be down, come up, it's going to have to turn. How high it goes, I don't really know. I can figure that out, but I don't need to for a sketch. Then it's going to come down. I know it's got to go through that negative 30, and to go through 3, it's got to come back up. And there's my quadratic, or excuse me, my cubic. All right, this is called a rational function. Now, you may not have gotten to rational functions if you had Mr. Carlin last year. Okay, I had asked him about this, and he said you guys didn't get to it. So, what a rational function is, it's got a variable that's in the denominator. So, this is what the parent rational function looks like. It's got these 2 branches. So, this graph up here is some variation of this. Now, we're going to go into rational functions more down the road. So, if you don't quite get this, don't worry about it. You don't have to master it at this point yet. All right, one of the things in order to graph a rational function is you got to figure out where the asymptotes are. Right now, this y-axis is what we call a vertical asymptote. The graph does not cross the y-axis. It just gets really close to it. Okay, where the vertical asymptote is located depends on whatever the denominator is. Whatever makes the denominator equal to 0, that's where the vertical asymptote is. So in this case, the vertical line x equals 0, which is the the y-axis, is the asymptote. This is the same as the y-axis. So to get the asymptote on this graph, we're going to just take the denominator and make it equal to 0 and see what we get. Okay, so the asymptote is going to be at 2. So at x equals 2, I'm going to have this imaginary vertical line that the graph doesn't cross. Okay, so what that means, guys, is this portion of the graph right here has got to slide over a little bit, and this portion of the graph is going to slide over. Okay. Now, this also has what's known as a horizontal asymptote. That's the x-axis. Okay, and the way there's shortcuts to figuring out where that is, and it has to do with comparing the degree of the numerator and the degree of the denominator. All right, the degree of a number by itself is the exponent on x to the first, or 0, is 1. So 1 times 1 is 1. So the numerator here has a degree of 0. The denominator has a degree of 1. So when the degree of the numerator is less than the degree of the denominator, that automatically makes the x-axis the horizontal asymptote. And again, we'll do more of that down the road, so don't worry if you don't get all of that. But all that means is that the horizontal asymptote would move it up and down, and in this case, it's the same. So it just stays like that. Okay, now if I wanted to get the y-intercept of this, so to get the y-intercept, you let x equal 0. So I got 2 times 0 minus 4. So the y-intercept is going to be negative 1/4. Okay, so this curve right here would actually go through negative 1/4. So I didn't do a really good job there. I should have drawn it more like, and then this guy would be, if they're just reflections of each other, this guy would be tighter too. But again, a sketch is, this is fine, this is good enough for a sketch. You would just say that this is 2, and then you'd label that point 0, negative 1/4. All right, so what I just did is what you'd see if you clicked on the answer of each one of these. It would take you through the same process. And again, don't freak out if you're like, oh, I don't remember any of that. We're going to touch on this more down the road. All right, sometimes a function is defined in sections. Okay, it's not confusing as it may look at first. This is known as a piecewise function because it has different pieces. Okay, which piece you use depends on what your input is. Okay, so this is a piecewise function. It's made up of 3 pieces. So this is the same as saying I've got a graph that is y equals 2x, a graph that's y equals 6, and a graph that's y equals 24 minus 2x. It's the same thing. All right, the only difference is here, instead of using x, they're using a t, and instead of using a y, it's using a v. So this could be like a velocity time graph, you know, of a vehicle or something. All right, so we're going to take each part of these. So my first equation is y equals 2t. Okay, so I'm going to take y equals, whoops, not y, I shouldn't say that. This is the same as v. Y is v, so this would be v equals 2t. Now, the borders of this are 0 and 3. So I'm going to substitute those two numbers into this and get a set of 2 points. I know this is going to be some sort of line because the biggest exponent on it is a 1. So when I substitute in 0, I get, when t is equal to 0, then v is going to equal 2 times 0, which is 0. So I'm going to plot the point 0. All right, when t is equal to 3, then I'm going to have 2 times 3, and that's 6. So I'm going to plot the point 3, 6, and then join those with a line. And then that's going to be my graph for that section. Right? Now we do it for the next section here. Okay, now this one's pretty straightforward because it's just going to be a horizontal line. So V is equal to 6. So when I take these values for t, there's no place to put them. The y value is always 6. So this is going to have the point, it's going to be made up of 3, 6 there. And then when t is equal to 9, v is still going to be 6. So 3, 6, hopefully I counted right there. 3, that's 9. Okay, so that's the middle one. And then the last equation is v equals 24 minus 2t. Okay, the lower boundary number is 9. So when t is equal to 9, v is going to equal 24 minus 18, 6. So that's the point 9, 6, which is right here. And then the last point, when t is equal to 12, I'm going to have 24 minus 2 times 12. And that's 24, take away 24, so v is 0 when t is equal to 12. And there's my graph. All right, the next part is we're going to go over how do you add and subtract functions. So to add and subtract functions, you're simply adding and subtracting like terms. So there's our example here. So if I'm going to add these two, if I'm adding two functions, I'm adding the like terms. So let's see, both of these are like terms, so I'm going to add them. Okay, that's 5x cubed. Okay, both of these are like terms, so I've got 3 plus negative 1, which is 2. Okay, these are like terms, so I got negative 2 plus 1, negative 1. And then these constants are like terms. Negative 1 plus negative 1 is negative 2. And that's how I add two functions. All right, the second part of this is to subtract these two functions. All right, so I'm doing the same thing. I'm just adding and subtracting like terms. So I'm going to subtract these two terms. Okay, so that's 4x cubed minus 1x cubed, 3x cubed. Okay, 3x squared minus negative x squared, the same as plus, so that's going to be 4x squared. Okay, negative 2x minus x, so negative 2 minus 1, that's negative 3x, and then 1, negative 1 minus negative 1, so that makes a plus right there. That's going to be 0. So there's the difference of those two functions. So on this next page, you're doing the exact same thing. You're combining like terms, or you're subtracting like terms. When you have to put a square, you're going to use the at symbol. When you want to put in a cubic, use the smash symbol on your keyboard in order to make the exponent a 3. So I'm going to pause this, go ahead and work through these, and we'll come back and see how you did. So this was just a matter of keeping all your like terms together. So I color-coded the terms that were alike and just grouped them together to make you be able to see how I combine those terms. But that's adding and subtracting functions. It's just adding and subtracting like terms. All right, the last one is you're given one function and you're given two functions, I'm sorry, and it says solve f of x equals to g of x. Okay, so that means you're going to take f of x and you're going to set it equal to twice what g of x is. So let's take a look at what that would. So I went ahead and I substituted in the expression for each one of those functions. Okay, next I'm going to distribute the 2 through function g. Alright, so we've got it distributed and I color-coded the like terms. So now I'm going to move all the terms to either the right or all the terms to the left so that I have the terms on one side and 0 on the other, and then I can solve it. Alright, so, and it doesn't matter which way you move them, okay? I'm going to, let's move everything over here to the left. So when I subtract 2x cubed from that, I'm going to get 0. So that's gone. When I take away 2x squared from both sides, I'm going to get negative 1x squared minus 8x minus 10. Okay, now I'm going to add 8x to both sides, and now I'm going to add 10 to both sides. And now I want to factor this and come up with the roots. Now it would be easier to factor if I didn't have that negative. So I'm going to take all of these terms and move them over to the right side and put the 0 on the left side. So now it becomes this. What two numbers multiply to be negative 16 and add together to be negative 6? Well, negative 8x minus 8 plus 2 equals 0. So I said each one of those equal to 0. So one solution is x equals 8, and the second solution is going to be x equals negative 2. So that's the two places where these graphs have in common. If we graph these two things, we'd see that they intersect at these x-coordinates. So I'll set that up in Desmos and I'll show that to you. Now to solve this with Desmos, what we're going to do, we're going to put in f of x into Desmos, create a third. Okay, all I did was, because it's asking us to solve where does this equal 0, which means where here's what that's going to look like. Okay, over here I graph, there's f of x. Now we don't want g of x, we want 2g of x. So on my next line, set up a third equation here, and I'm going to say I want to know where is this equal g of x. Where does this equation equal 0? Where is this a 0? And you can see, so I could solve it graphically as opposed to algebraically. Alright, and that's function notation. So now you'll do lesson 2.2, the online assignment. And we'll see you next time.